Good afternoon, good morning all, wherever you're from or wherever you're reading and watching this. Welcome to the semi-monthly, I guess, bio webinar sponsored by LBG Medical Customized Devices. Stuart Roseler here, the consultant within the group. We're going to talk about materials and mid-layers. 2 months ago we talked about materials. And because it's such a huge topic, and some may say a fairly dry topic, some may agree, we talked about the shells or the base materials, things like carbon, polypropylene, all of those types of stuff. This section of the materials review is on mid-layers, or what we refer to as mid-layers. Some of you out there might know them as padding or anything else, the stuff in between the top cover and the shell material, the base. So again, it's a brief review. It's looked at popular padding. There's a huge wealth of information out there. Okay, well, let's get started. It's fairly full content, but this is a bit of a map of what we're going to look at today. Quick review of where we've come from. So that refers back to the materials lecture that we did, as I said, a month or so ago. You can find that on our website, lbgmedical.com, and go in and look for education and or videos. And you'll be able to see webinars in there. There's a whole swath of stuff in there. I appear in there and my colleagues as well. So we'll have a look, then we're going to have a look at the mid layers, and I've sectioned them up into what the mid layer is doing in a physical sense, technical and physical sense, and 3 main areas there. It's padding, how it redistributes forces, and considerations about the shape. From there we go into the compositions of the mid layers that you can use. Again, this is where it gets quite technical, so I've tried to make it as simple as possible, and of course to do that I've had to focus on just a few key popular materials or interesting materials that are out there. The same process can be taken for all of the stuff that you use or look at, but it's the terminology that you might become familiar with through this. And then how our brains go through and select these materials for the clinical outcome that we want, and that's the main thing. Okay, so again, such a big topic. It's not an exhaustive list, and the materials out there, they can change. You can change one little molecule component and it'll change its properties. So this is a forever big topic, and I can completely understand why people out there get confused about what's going on. But you start to see patterns in the different styles of materials that are out there, the types and brands. Again, complicated and content rich very quickly, so I apologize out there. I quite like it, but I do have a lot of conversations with people that do get fairly confused fairly quickly, and I understand, we all understand there. This is what I do. I know some of you out there that talk about things that I don't understand, I get lost very quickly. So it's a good quid pro quo. Here we go, Plastic Man. So this is just reviewing what we talked about before. Okay, this is the power of ultimate variation. This is my sense of humour getting in there and letting you all know that there's no one right answer for this, and plastics are completely at our disposal on what they want. So it's such a fantastic thing to be able to do with a material, but also that's a bit of its curse. Because there is so many variations, sometimes we're getting things that we don't really understand why in our clinical outcomes or what the materials have done over time, all of this type of stuff. But it's the slight variations even between what we call the same material, because different processes can affect them. Again, not going to tell you what material to use. This is pretty key to these series. We've all been trained as professionals to go through, collect as much information as we can. We start, I call it an upside down triangle that turns into that's a triangle. So our professional process is to collect as much information that we see as relevant to the topic or to the problem at hand. We then use our judgment to evaluate it, and then we consider what the different options there are. We then apply, and most importantly, we review. Have we done what we thought we've done, and is there some time to go back and collect more information or evaluate in a different way? Okay, so that's the process that I want you to think about. Again, materials is one part of a bigger school of thought. This is just a materials review. The shape of orthotics, the symptoms that you do and how best to marry these materials and the shape, your preferred way of working. Okay, it's all part of a design process, which is a big and rich field of study, and that's where I lie. All right, we're just again referring back to what we did last time, and again a quick review. Forces, you've got internal and external forces that work on the human body. Okay, you've got your shear internal forces, you've got your tissue stress theories, and then you've got external forces that are your ground reaction force that cause the distortion in the tissues. And then going back to pure physics, these are the different types of forces that we talked about. You've also got pressure, and I distinct pressure away from force, really. It's an interesting thing. Pressure is more of a descriptor, an umbrella term of the different types of forces that can occur. But again, there's lots of academic discussion to be had about the definition of that. All right, but the main thing is pressure. It doesn't have a definition, and it relates to the surface area that we're dealing with. So in podiatry world, that's a small foot with a cavus profile. We'll have a lot more pressure come down to it for the same weight person that's got, say, a pes planus foot that's spread out in different areas. And of course, when we change the position of any of those, if we can, we change the pressures at any given area. So that's how we determine what we'll get at the end of the line. And then of course you've got similar areas that look at the forces, and you've got relationships between stresses and strainers, your stiffness, your elastic limit. It goes on. Creep's an interesting one. We see that quite a lot in how we use devices long term, and that can be a consideration for what we use, particularly in the mid layers. Okay. Back to mid layer. Look, we've got here so far. There we go. Tick the first one. Next one on the line. So this is a review of a slide that was in the previous at the previous discussion. So we went through base materials, and you can see how that was a fair summary, but quite complicated. We're at the mid layer padding stage, and I've considered it the mid layer. It's those things that you want to combine between the base and the top cover to produce something that fills a space and or sits in a space and or doesn't fill a space. You want it to be as low profile as possible, but the quality of what you want in there, basically, in a very basic sense, you want it to absorb or return energy or dissipate it and move it in some way. Okay, so it's the energy return that we're looking at, or the energy dissipation, or the energy absorption of everything that we're doing. This is generally where mid layers can affect it, and we'll go and talk through that. Of course, the base, the top cover, and the posting can all influence this as well, but for the simplicity of just discussion here, that's what I've looked at. Anyone out there thought, what is a mid layer for? Okay, as soon as you ask questions like that, you start to go, well, do I need one? Is it, is it related? Is what's presenting in front of me in that clinical, profile of a patient that comes in? More often than not, we're looking for cushioning or comfort. Okay, but if we go into the dictionary, okay, and we look at a mid layer, and we again refer to it as padding. It's a soft material such as a foam or a cloth used to pad or stuff something. Okay, so padded up, padding. I didn't quite like that, but it's interesting to think you don't really want to stuff things in your life, not in the literal sense, but it's essentially something to fill a space. All right. What does it mean in orthoses? Again, smiling, I don't want to stuff my orthoses, but if we want to pad or stuff something, we want to assist in the management of the impact energy. Right, that's what I'm thinking of when I look at a mid layer. Okay, is there an impact energy? Is there's something that the ground reaction force is applying in any particular case? Sometimes people move in a certain way because they can't put enough energy into a certain spot. And my philosophy of orthoses is to try and redirect that position into a more appropriate, less pathological way. And that may not be anything that we've seen before with that patient. So It's just management of that process. There's a concept in physics and engineering called duration time. So essentially, forces can't be created or destroyed. Okay, they can only be moved to somewhere else, and that's quite key when thinking about the biomechanics of foot orthotics and what we're designing. Okay, so in this area, what we're trying to do is reduce or extend the amount of time that force is put over. Okay, the concept there is a hand clap. If you clap your hands really fast and really hard, the duration time is quite small. You make a loud noise. You feel you hear or feel the force in your hand, and that's all the energy going from one condition, the moving hand, to another condition, the stationary object between your hands, and it gets generated in slight heat, noise, and obviously response, shock waves, and whatever else. Do the same thing. You slowly meet your hands together. You extend the duration, the time that the energy has to dissipate through. You're not going to make the loud noise or feel the pain in your hand. Okay, so it's more like a clap as opposed to a push. Okay, and that's what duration means. So again, in mid layers, what's the duration trying to do? It's trying to capture it early and then control it through a process, right? And that brings a sensation of less hurt, comfort, padding, cushioning, whatever you want to do. All right. The next thing to consider is it wants, again, to redirect the forces. Okay, closed system, we can't change the forces. We want to redirect those forces that we talked about before in a kinetic sense. All right. And it's also, again, this is a bit hard for beginners out there to think along. Forces are a thing that we describe. Okay, we describe the force and we try and move it, but the motion of that object from the force is something called kinematics. Okay, and so what mid layers are trying to do is create an alternative motion of the foot. So yes, redirect the forces that may come through shear, stress, compression forces. Okay, but the motion through an arc of movement is also what can be affected. Yes, this can be affected by the shell or the base material of the device. It can be affected by the top cover. Okay, it's probably the shell that does most of the work, but again, we need to consider this for the mid layer because it can and does affect what we're doing. It all combines. Next thing I'd do outside of looking at what types, where the forces are, what we're trying to do with the orthotic, what type of forces are we trying to deal with at any given case? Okay, this comes now back into what's my patient profile. Are they a basketballer, jumping up and down a lot, twisting and turning? Okay, so probably the two forces there, you've got peak ground reaction force when they land, and a shear force that may be going when they stop, twist and turn. Okay, the netball 2 steps after catch is a typical of this. Or are they just someone that wants to do a lot of hill climbing, okay, or incline walking, right? A lot more shear forces, possibly higher impact forces as they get more tired, okay, so their muscles fatigue, they're relying on the foot to dissipate more energy than otherwise would come along. That's a part of what Benno Nick is talking about, the adaptation there. And or what materials are good for both of those situations, as opposed to you and I going for a walk for a coffee on a Saturday afternoon. Okay, we may be getting pain in that position, maybe from a bony or a jointy condition. What do we want to try and do? Stop ourselves getting in that position for that period of time. Okay. And of course, washing that all over, the tissues that are involved with that, you know, skin, muscle, ligaments, joints, all of these different serous fluids that can occur in between and around. The mid layer and what's going on there and how it behaves over time is what we're trying to do. This comes to the fore when we've got the high risk wound type situation, when we're trying to deal with different types of tissues that are under stress. And of course, acknowledging that the natural, normal, healthy muscle versus an aggravated, irritated isis or osis of a muscle or tendon, ligament, behaves very differently to what we think it should understand, and our role is to try and get that soft tissue to come back into the world of where it should be. Okay, and we do that for a period of time. This is how we do it, through our design and consideration of materials. Okay, And then there's a temporal consideration or a time. If we're playing basketball once a week, the orthoses that we're considering for that activity may not be reflective of what is the best benefit or outcome for that patient, considering they're playing it once a week for maybe an hour, whereas the rest of the time they're on hard surfaces in an industrial setting. Okay, so different profiles, different considerations, and think about, well, when do we need these devices? And possibly we need more than one for the same purpose, okay, depending on the engagement of the patient. And then, of course, our goals. What is it we want to occur in the padding material over time? So not just the patient, but in the material, acknowledging that some materials are actually designed to move. Plastazode is one of those, so they're what's called an open cell structure. It might be closed cell, I'll come back to that. But the concept of that material is to change over time. So this is definitely engaging with the patient to say, look, we're doing this right now at this point in time. This is when this material is designed to do this, but going forwards, it will change. It will become more comfortable. It will become less comfortable, possibly. We need to have an engagement with the patient to come back and acknowledge that this is a process. It's not a one-stop shop. It's not, here you go, take these, don't come back. We need to acknowledge that this is a therapy over time, not a solution to a problem as such. And again, what changes in the shape. So coming back to, yes, the material can do a certain thing, and generally they're all tested on a flat surface with a steel ball that drops on them. But what does that mean in relation to us and our curved surfaces and how the body moves and all of these different considerations that go on? Okay, so ideally we can think, yes, it'll work this way, but in realistic terms, it may not behave how we think it will. And we learn over time how that happens, but that generally is a private personal process between clinician and clinician themselves. So it's very difficult, but it's worth getting right. What changes over time do we not want? Okay, consider that. There might be a risk profile there. We cannot let this thing happen, so we cannot use that material because we can't guarantee it won't change over time. Okay, so they're the types of things to think about when we're looking at padding or fill. All right, the next point of a mid-layer and the consideration of that is its redistribution. Okay, so this first topic that we've talked of here, okay, sits in what is a mid-layer for, okay, pad or stuff something, we go into now, okay, what is it doing in an energy sense, right? Ground reaction force, GRF commonly known as, part of what the mid-layer can do is redistribute this, and this can be seen at the first MPJ. Okay, generally the orthotics finished its effect. The shell has finished its effect. The shell's almost put the foot in a position to move in a certain way and redirect itself to there. But as soon as we get to that toe-off position and we want movement there, this is different for a hallux rigidus type profile, of course, but as soon as we get that function of the first MPJ, the distribution of the ground reaction force behaves differently, of course. Yes, we've set the foot up in a way, but there might be something going on that happens right there and then. All right, so everything leads in a sequential chain of events that occurs to get there. So this is just to show you, that there is a force that we apply downwards, okay? And of course, in an energy system where everything has to be opposite and equal, there's a force that responds to that upwards, okay? So it's in a technical sense, it's more about the ground reaction force that occurs, because that's the measure that we can get. Right, the blue arrow can change over time, but the ground reaction force is always going to be opposite and equal to it, unless we're the Hulk. So padding can affect this. Again, this can sit in the world of posting, shell material, not so much top covers, but definitely in the shell material. This is really what they're designed to do, but we need to consider that a mid-layer will and can affect it. And that's where we think we might want to put a heap of padding there, but it will change the way that the foot moves. Okay, so we've got this ground reaction force. We want to reposition the size and direction of it, okay, to the next part of the foot it was. There's just a little picture here to show you the center of gravity that is technically going through the foot. And And you can see that the center of pressure as we strike the ground at the bottom of the heel, it then progresses slightly outwards in a theoretical sense, and then in an ideal theoretical sense. And then as it moves inwards, it starts to go between the first and second intermetatarsal space. Okay, what is ideal? What is normal? And that's for a different topic of discussion. What we're trying to do is, if we want to change it because it's clinically what we want to see, how do we do that? And the mid layer and the selection and the type of mid layer material that we're using can affect that. Okay, so it can be good. You may not want to do it in the shell because you can't, or it may be too much for that patient to bear. So as an interim measure for the next 6 months, we're going to put in a medial pad, okay, that may take some of this pressure away. Do we do it with padding? Do we do it with the shell? Do we do it with the shape? Okay, this is the core of what I'm talking about in the mid layer. Okay, so when we redistribute these forces, of course we need to consider what they are. All right, compression, shear, torsion, and bending are the ones that come to mind, and that's just an example of those. All right. I also consider in my kind of operations, the foot is naturally an organic product. It's in a closed system generally, and generally we're moving and walking in a certain way. So a lot of the materials that we use will not be the best, most ideal thing that they can possibly be, because they're designed to be hydrophilic. Okay, they're designed to manage moisture or get it away or get it. Neoprene in one of these things is a classic example. It's really good properties. It's a synthetic rubber kind of profile, but it tends to get sweaty and it doesn't allow water to flow through it or breathe out. Okay, so it can then get smelly because the little microbes get in there and like it. So over time, we need to consider that. And of course, just engage with the patient. This is what we've chosen today. It may wear out, okay, may change. The shape of the device is a bit harder to consider. Now, I've thought about this in just my background and experience in life, I guess. I'm a skier and a surfer, and I like those types of things to do. When we look at the shape of the device, we've got an arch, okay? The arch is a very strong structure in life. We've considered greatly about the shape, okay, of this arch, and more so on how it feels. Because that's the response. We need to get this feeling so the patient will wear it. It's no use if it's too high or too low, they won't get the effect that we're looking for. So when we consider the shape of an arch, there's a lot of mathematics that goes into it. Okay, it's as the force that we press down, okay, the forces get redistributed in a way that we can then use to manage the foot. Okay, but of course, remembering that the concavity of these curves will impact the ultimate force that will return, that ground reaction force. It'll change, right? So if we're putting a padding or a mid layer on there, it's going to change the shape of the device, which will then change the force available in that area to advantage or disadvantage. Again, it's just about more of a consideration point. And of course, when talking about arches, we need to acknowledge that they're at 3 positions in the foot. There's different arches. Okay, there's a medial, longitudinal, lateral longitudinal, and transverse arch, and that's what I say there. Now, they don't exist in 3 distinct places. What you need to think of is a surface area that it goes from one shape in the medial arch, say, and then it translates gradually into the lateral shape. Okay, this is just 3 points in time that we say, well, this is a reference point that we want, but that shape can be ultimate variation between. All right, when we get a met pad and we get it in the wrong position, what we're doing is affecting that transition from one point to another, and that's why they're so challenging and so uncomfortable if they're not referenced in the right position. Okay, now consider the force that's returned because of that shape. In a simple sense, if we have a high concave shape, a high arch foot, let's assume that it's a high cavus size 9 foot, the force that you return because of the arch is going to be a lot higher. Okay, now let's say we've got that same foot, but we've casted it in a weight-bearing position. Okay, natural, completely understandable. Again, I won't get into the academics of non-weight bearing versus weight bearing casting techniques. That's for the practitioners themselves to decide on what they want to do. But when we look at what we're trying to do long term with the device, we need to know that ground, okay, as clinicians. So we've got a high arch, high cavus shape. It's going to return a lot more force at any given point along that line than something that's more shallow. Okay, so the shape will return a different force if it's a lower arch. Okay, and the concept here is to think of squeezing an egg. If you squeeze it end on end, that concave shape is a lot higher. The forces are redistributed. It takes a lot more to crush that egg under that way than if you turn it side on. Okay, if it's a side on egg shape and the arch is a different shape, it will crack generally quite easy. All right, so that's that same one, and we need to consider that when we're talking about orthotics, because that's the response that the patients give back to us. Oh, this is too high. This is too lumpy. How do we get that shape? It's our casting technique. Okay. The risk of poor casting technique is manufacturers as a whole want to sell more product, so they may reduce the arch height without you knowing it. Okay. That's a very challenging and inflammatory response to say, okay, and what we've got to do as clinicians is say, well, no, I don't want you to change it unless I know. I need to know if I'm casting in a certain position that I need to control of it, okay, because it will start to reduce the arch height. Simple thing is have a consideration of how high you want that foot in that position to have its arch in that shape, okay. Always look at your casts, always look at your scans. Okay, now with the shape, and we're just focusing on the shape of the arch through the mid layer or through the shell material that is, again, consider the transfer of energy that originates from a curved shape. This is something that they refer to in ski world, I guess, as the fall line. Okay, you've got a fall line as a hill. It's a bit of a rough parallel. But what we're trying to think of here is as the shape of anything will dictate the fall. Okay, the idea is if I fall from a plane without a parachute, all right, who knows whether parachutes work or not, they've never tested them. But let's say I fall from a plane without a parachute and I hit a flat surface, okay, no curve to it. All right, I'm going to be splat. It just goes down there. Now imagine, if you can, that I've got a very, very tall skateboard ramp, okay, extremely tall, stories and stories high. It starts at the vertical and then slowly transitions itself down to the horizontal, the flat. All right, that's the fall line essentially. As you go down, you're going to have less downwards pressure, and it's going to be transferred. The energy is going to be changed into a horizontal energy, okay, which then means there's less impact against the ground on the horizontal surface. So essentially I slide off. Of course I get shot out the end at super power speeds, but hopefully I can manage that a bit easier. The same concept, believe it or not, is when you're surfing. Okay, surfing is essentially a controlled fall, and so is things like skiing. Okay, surfing is a bit easier to see because you can see that shape, and essentially that cool dude there surfing away wherever he is in the world, having a nice time. Okay, he's essentially falling downwards. That's the gravity is applying to them. It's the wave shape is actually then pushing him forward. Okay, that's a very simplistic way of looking at it, because there's interaction between water molecules that are compressing and pushing and carrying on. But if we just think of that shape of falling down gets transferred into falling across, and then that mitigates the pressure that's going there. Okay, the ground reaction force. Okay, so then when we look at shape, you've got the height, width, and position of paddings that can affect it. Okay, of course, it changes the shape. One thing that I want everyone out there to identify is who references where the padding is positioned. Okay, is it us? Or is it someone that we just say, put it in the same spot that you always put it? Okay, this is a unique patient. They've come into you in a unique situation. They might have a size 4 foot, but it might be a really wide foot. They might have a size 4 foot. They might have a really narrow foot. They might have a size 4 foot with some sort of metatarsal parabola that's changed. Okay, all of those things are privy to you and that person at that point in time, because you've got the objective, you can look and poke and see. Okay, as soon as we then translate that to any other person in the chain of manufacturing or orthotic, do they know where to reference the things to put the pad on? Right? They might say, we'll do it in between the two met heads. What reference do we use for the met heads? Okay, might be simple and clear, but unless we as manufacturers know exactly where to put things, the errors that occur are seen with us as clinicians, okay, in a met pad position being in the wrong spot. All right, so, and it happens more often than it should. So the kind of responsibility there is between two labs to have a clear understanding of what's required of them, but us as practitioners to give good, clear, accurate references of simple things that we have all been taught at uni. Okay, to do this, pictures help. Again, reference points help even more. If you can put a reference point on there, we can then, or the manufacturers can then reproduce it to be exact and then go from there. All right, and again, this is all important because it's the mid layers that we're talking about and the position of them, getting them to work. Well done. If you've got through to this point, that's quite a lot. This is actually where it gets a little bit heavier, but we're on the shallow end of the slope now, so we're kind of sliding in and getting more horizontal as it works. So compositions, okay, typical compositions. Again, this is a bit of a repeat of what we've seen before, but you've got again polyurethane, the two at the top. You just consider that they can come in two different processes, okay, elastomers or foams. All of these materials can come in different processes, but in general, in orthotic materials, this is a brief list of what we looked at, and that's was done by Rome back in 1990. So polyurethanes, again, just an example of the different processes there. We've got polyethylene, again, it's a foam, same process, different material, and then they're the brand names that sit next to them. PVCs, PVAs, okay, synthetic rubber foams, and then you've got your silicon rubbers that Rome discussed. Interestingly enough, didn't put in polypropylene, okay, which is again not so much in materials, well, you'd think, but we'll go through and have a look at that now. So polyurethane, PPT plus, okay, commonly known as PPT, and then you've got again, sorry, this little section here just refers to those that are generally just used as padding, okay, because you can have a combinations where it's padding and top covers, which gets a bit complicated, but for this purposes of this, I'm just discussing the padding or the mid-layer compositions of these. So you've got 3 or 4 there, just 4 that I could think of off the top of my head. Generally, they're not applicable as much to be a top cover by themselves, whereas this one is. Okay, so, and again, this is typically what we see in labs. It's not an exact thing. You have more or less in different positions, different supply chains, everything else. A word of caution is that if you ask for PPT, there's an inordinate number of PPTs out there that with just slightly different chemicals from different suppliers. Okay, so get used to what your lab produces and work with it. Okay, as opposed to seeing differences that are very hard to track or trace between suppliers. Poron's the same. Right. So the ones that were reviewed here, okay, that's just this list combined down, and I just picked an interesting one. You can see that Poron survives in there quite a lot. It's probably because it's quite popular and it's the one that everyone thinks of when they put in. But again, PPT is polyurethane foam. All right, Poron is a slightly different combination. So Plastazote. This one I stuck in there because it explains a good offsuit of them, but Plastazote can be quite good for those situations where you're wanting direct body contact with something that's a bit gooey. All right, so that's our point down there. It's open wounds and lesions can be dealt with Plastazote because it's a really quite stable material. Anyway, I digress. When we start to talk about these different mid layers, we talk about closed cell and open cell foams. Okay, so a closed cell foam is like a little bubble that is a bubble by itself. It's got bubbles next to it, but it's closed to the other bubbles. Right? The open cell form of it in a foam is the cells are more regularly open to the other bubbles next to it, so they share. And this is typical of what you see in the sponge that we use in the sink. Okay, you can squeeze it, it's quite soft. That's classically what we call an open cell design. Whereas a closed cell one, if they were all closed, you would squeeze it and it would resist. And so that brings back some of its resistance to the energy that we're putting into it. Okay, so plaster cell is interesting because it's a closed cell foam, so it'll get to a point and won't go any further, but it's cross-linked and the space between the bubbles is a bit more open. All right, part of its power, I guess, in orthotics and orthotics materials is its skin contact material. Okay, like I said about the open wound type ideas, it will handle those a lot better than a lot of the others. Okay. Just considerations when we're using it for what we do. Okay, readily heat laminated, most plastics or thermoplastics are. Okay, that creates a thermoplastic. The range that we use it for in orthotics and orthotic manufacture, or orthoses, is different densities. Okay, generally it ranges from about 40 to 100 kilograms per meter squared. But when we look at the different types of devices that it would be used for, again, what are we going to use this product for? If you're using an accommodating device for that, say, high-res foot, you'd probably want a mid-layer or mid-layer top cover, because it's a combined one of those in a low density up to the high densities, depending on the profile that you want. Okay, so typically low density 33 up to a high density 115. If it's used in supports, okay, so this is more in the shell materials as a replacement for a shell material and or others, you can use it at the higher ends. If you're looking for it for a compressive thing, so I call this in my language a sacrificial thing. So I want it to be on there, but I want it to kind of compress early to give that lovely contoured shape with the shell underneath the device doing the rest of the work. Generally, they don't range from any higher than 24 to 45 low density compositions. All right, and that's what it will, again, pressure kilograms per meter squared. So it's a weight over a surface area. Again, the ones that are suitable for direct body contact and a thing called direct body molding, which is where you can heat the material and apply it to the body quite quickly because of its low thermal conductivity. Okay, so that process you can heat it up quite well. It doesn't take too long for it to cool down because it doesn't absorb the energy of heat too well. Or too much, and then you can shape it to what you need. So it can be quite successful in those. But again, it doesn't last too long in those areas. And the other thing that they flag about it is it's quite lightweight. Okay, make your own decisions on the weights of the devices that you need. Polyurethane, PPT, okay, quite popular, open shelled structure. Again, we're going back to that idea that it's more like a sponge that we use in the sink, right? But processed in a different way, that it's actually a little bit stiffer than some of the low densities plastozotes that can be used. All right, this polyurethane, okay, in its foam form that we use, is extremely versatile material. Polyurethane is in everything. Okay, disrupts probably. You've got many hard. Look at the plinth that you've got in the clinic. That's probably polyurethane. Or some kind of rubber composite wheel that goes in there. When we look at the total uses for it, it's only 0.7% of the global use, and that's for footwear. Okay, footwear, which includes all the shoes. So orthotics is minute in a sense, but you can see how much it's used, more so because we use it all the time. It's got good cushioning profiles. We'll talk about cushioning in a little bit. It's okay for shock absorption when compared to the others. Right, this is probably early days when we used PPT. It was the best out there. Now there's different combinations of things that are out there that are much better at attenuating that energy out, so they absorb the shock. It's got good abrasion resistant properties, but the research in there has generally come for when it's applied to things like steel. So it can be pretty good over time. Definitely compared with the other types of padding material that we use. And of course it's stable. Most of the thermoplastics and plastics and rubbers and foams that we use are fairly stable in a compound sense. That's more of a hark back to anyone that's knows of the old cars or left some of the porons in cold weather or sunny conditions. The old foam seats of the Holden utes used to disintegrate quite quickly over time back in the early days, because all they had was different types of thermoplastic compound, whereas nowadays they've sorted all that out. Porons, so this is in the poron zone. Again, it's an open cell foam, but it's interesting because the way that they've put it together, it's wound in a loosely spring shape. Okay, so it provides both cushioning and bounce or energy return. Okay, and this is, again, I'm very conscious of the marketing that goes on here, but it does tend to have good profiles there. It cushions, okay, and so when we look at cushioning, it is something that returns, or doesn't return the energy, it dissipates it. Shock absorption dissipates it even more, and energy return is the bounce, right? So Poron Vive is a good cushy bouncer return, right? Absorbs and returns. It's got pretty good shear abrasion resistance. If you've got any product samples that you've got or offcuts, just get this material by itself and try and tear it, okay? Without any fractures or cuts in the material beforehand, if it's still quite quality, it's really difficult to tear. Okay, so that kind of indicates that it's a good shear resistance. Hard wearing, we'll say it retains its shape. Okay, so it means it'll keep bouncing a lot, right? And it doesn't tend to dissipate over time. Okay, this was done in a test period. It doesn't describe what the test period was in the stuff that I found. And so 55% of the energy that the ball will generate in a let's say a meter drop, 55% of that energy was rebounded. So let's say 50% return energy is in bounce. So for those profiles where we're looking at someone that's possibly running or wanting a bit of assistance, okay, you can add this stuff and it'll last fairly well, and it can help produce the spring. Okay, word of caution there is, do you want the spring? Where does the spring go? What angle? There's no use having a bounce. If anyone has ever tried to sit on one of those big balls at a fun park, you jump yourself on it and then you spring off in a certain way that you don't really know. Okay, so it's all to do with the shape and how we apply our process of where do we want it. I know personally as a lab here we had issues with bonding, and that was to do more with the polish. We had a shiny surface on one side which didn't allow some of the bonding to occur. We've now resolved that. Okay, so if you're having any of those where the mid layers not letting the top cover or the base combine over time, it's unsticking, have a look at how shiny it is, and going forwards the suppliers have then corrected that for us. So going through there. Poron 94, again, the reason I've done this is we try and keep Poron as the same group. It's in the same family as Poron Vive. Open celled polyurethane, cushioning, and slow rebound properties, shock absorption. Okay, so it's virtually the opposite evil twin to Poron Vive, or good twin. This one provides cushioning and shock absorption, not bounce. Okay, so when you drop the ball on it, the ball doesn't bounce at all, or hardly any. All right, so if you're trying to attenuate shock in a tissue, it will absorb that energy quite well. All right, it's got, again, good resistance, same as the porons. This one's mostly those ones where you really want that muted effect. You're not looking at energy bounce, you're looking at shock absorption. Right, again, combine that with Vive and a double mid-layer combination, look what you can do. You're probably negating each other depending on what you can get. It's quite good at managing all the waters and moistures that I talked about, and it's got good internal strength. All of these things, as I said, apply to porons. XRD, okay, this is just the bigger brother of Poron 94, not just. It does 90% of the impact at speed. Okay, so going back to this duration concept that I talk about with clapping our hands, 90% of the energy, high impact, will be absorbed, so it's the impact energy. Whereas if we go back and look at Poron 94, that might be a slower duration. Okay, so slightly different conditions, slightly different considerations. Obviously, there's a different cost involved with all of these, but it comes into, well, what is it specifically that I'm going to do, and does it work for me? Right? Is it too confusing, or do I need it? It might be, yeah, I'll do that just in this case, but it might mean that it won't last as long as the other stuff. Okay, so there's no one right answer. This one doesn't have as good shear resistance, which can be, you know, blisters and stuff like that aren't managed as well. But again, it combined with other materials and other top cover type ideas, you can easily get around that. All right, and the rest, as I said, is the same as the other porons. But this is the one that absorbs most of the energy. It's really quite you hardly hear any now. Hardly hear any noise, and it dissipates the energy so that the ball doesn't bounce. There's a good example of that. When we go out and see people, we can drop balls on things and they can get an idea of how it works. EVA, okay, polymer foaming production. Again, we talked last time a little bit about how polymer foaming goes on. It essentially is injected into a semi-molten EVA, and the different bubbles occur. All right, so we've got the bubbles. It's essentially what we traditionally would see as rubber, all right, EVA, but this is in a top cover sense now. So it's the same idea. Very good resistance to most everything, and it's quite a popular, stable material. Really easy to work with. Tends to compress a little bit more over time. But again, I look at all of these things as what are we trying to sacrifice for the movement that we're trying to do. And if we've got a pathology, we need to be reviewing that it's working long term. Okay, short and sharp early days, get the things under control, see what we're going to do, get the patient used to this, and then use different things longer term to know that they're going to wear, but they're going to wear in a controlled way. And all of these recyclable. Okay, this is really quite hot nowadays. I'm creating a bit of a focus internally here to make sure that we are clear on how recyclable all these things are and what it means to remake devices. Okay, so watch this space when you kind of something goes wrong. So the reason we don't want to get these things wrong is because we don't want to waste materials for the world, essentially, not just for a business process. Almost there. Okay, so now this goes back into our clinical process. What are we going to do when we select it? So you tell me, okay, which mid layer is right? Who knows? Okay, might be one of those things. My colleague Heidi Meckler did this a few years ago, where she got some research on responses of what people use. Okay, this is clinicians out there. I just find it interesting. I'm not sure how it is. The reason that Poron Vive isn't in there is because there was another material that was used for the same process. Okay, so let's call it that energy bouncy return type stuff. But you can see that at that point, the Poron was by far used. I would say that it's probably a mix of the Poron family that has now overtaken. EVA quite low. Again, this is more of a popularity contest. What do we remember? And to be honest, what do labs use when not told otherwise? Right. So it's just a matter of it's quick and easy to get the Poron with an abraded base. It wears well. It's defunct. It doesn't do too much one or another way. Again, keep things simple. And of course, then you can see generally how it all works. Just of interest, the EVA that is generally used in a top cover is a medium density EVA. You can get lower versions, but that's obviously on a different special request. And of course, carbon fiber type materials that go on, not very common. You see PPT's quite low down there for whatever reason, I'm not sure. Okay, but that was just this responses of 232 participants. So trying to help us decide which is the best material, LVG, and well, I've helped them develop just a quick clinical sheet that comes together. I have one of these sticking in front of my computer and desk where I'm designing my orthotics. And when I'm trying to consider for the patient, writing that prescription form, what's best for them, this is just a bit of a mind jog to what the different materials are. Okay, I've done this for a while now, and I know generally what they all are, but even I forget. So it's more about, well, what's new, what's the name, it's something different, Vive's the new kid on the block. What does it do? I can't remember. Whereas when I'm there and I push it with my finger, I go, yeah, all right, now I understand. That's kind of the touchy-feely that I want. So it's just trying to simplify this whole process so we can use it on our scripts. Again, this isn't an exhaustive list, but if you get in contact with LBG sales team and ask them for one of these, I'm sure the guys in the lab they love putting these sheets together for me because it takes them a long time. Again, we don't want to waste this material. To create these little swatches, it takes a lot of time and energy and also materials. Okay, we don't want to waste these because they are a finite resource in the world. Again, this is just a hark back to the hardness scale that I use for the shelves. The same idea can be used for top covers and padding. So I'll probably look, when I shave off a bit of time for myself to have a look at these things, I'll probably try and put something like this in the mid-layer section, all right, just so we get an idea of where the plastics and the rubbers and the different things that we've talked about in hard layers go there. That can also help us guide our clinical thought process, I guess, and then ergo our script that occurs that we present to a lab. And again, you know, it's all well and fine to ask someone their opinion with regard to what would they use, but it really comes down to the onerous task of us understanding what it is to use because we're the ones responsible for it ultimately, okay, as practitioners. We're padding materials, okay, so this is now just kind of to consider what to go for, what my thought process would go through when I'm looking at mid layers. Okay, what type of force is it that we want to manage? All right, shear, direct, impact. Where is the padding? Okay, what position? Please remember to put the references on everything. Okay, I remember when I was taught at uni, they almost a wooden stick. Where's your reference? Where's your reference? Where's your reference? In any material, that was Harvard reference, but again, to manufacture something, the lab techs need a reference point. And if they put it on themselves, we're in a world of hurt, okay, because who knows who's going to repeat that. One lab tech might do it for one device and then do it again for another, and it's in a completely wrong position. Right, the foolproof way is us as practitioners do it. That maintains our own internal quality, and of course it reduces the amount of us getting things that we're not expecting. All right, so the shape, so type of force to be managed, position of the padding, and then the shape of the device. Remember your casting techniques, okay? Don't just cast and think, well, that's an exact replica of the foot that I think. We always get it in a certain different way, and that's what the script's there for. So part of the casting is to represent what we want in the device, and if it's not casted in an appropriate way, the device won't be right, all right? To get around that, we need to modify that. I went into the design world and designed it 3D modeling myself, okay, but there's many other ways you can do that with a script form. The thickness of the padding, okay, again, if it's too thin, it won't do a lot of these properties. It's kind of like, you know, you can have a small cup of coffee, it may not do much. You have a big cup of coffee, it might do a lot, all right, but it depends on the strength. Right, but these, let's say the coffee is the same strength. If you have a lot of a really strong coffee, it's going to have a bigger effect on you. The same idea with the mid layers of materials that go on. All right, so thickness is a finite resource in a shoe. All right, we may only be able to get away with certain things. And again, material, what we're talking about here. Manufacturers and suppliers of these materials, they differ slightly. The way they're stored, the way they're processed, the way they're manufactured, okay, all different. It's like Colonel Sanders' secret herbs and spices. Essentially, you can't repeat it, but you can't change it. Again, I consider that the mid layer is something that's designed to compress over time. There are ones that are better at it than others, but this is a device that is designed to be used and worn. And how many pairs of shoes out there do you see that are older than 12 months? The durability of these things, you need to consider with your patients and discuss it with them. This is what I talk about engagement, right? So these aren't going to last forever. Carbon fiber has one of those lovely things where it won't change over time. So it doesn't mean it lasts forever, but it just says it won't change over time. All right, this isn't what a mid layer will do. It's got an operation of working within a design period. I think it's between 1 and 3 months. Okay. And then there's a kind of analogy that's used. If you leave poron in the car boot over winter, it disintegrates. Okay, so that's generally what we're talking about here. There's different durabilities for different combinations. And remember, where is good? Multiple combinations that can meet your needs. Right, put things together is ultimate variation here. Okay, you can get something that meets some other reason, and you just got to line it up with that patient. Okay. Again, what do you want to do afterwards? Do you want to reapply heat? This is particularly considerable when you've got that new patient and you may be still trying to get the perfect device. If you put a mid layer on there and then you go and heat it again, it's going to change it. All right, so we need to acknowledge that this is an early stage process and things aren't always exactly what they seem. And again, shock attenuation materials behave very differently depending on the weather. Me being a skier, okay, and then going in and surfing, I can't really expect that the rubber that I use in the ski boot will have the same materials that happens when I'm walking on a sunny day, you know, down to the beach. And again, the finite space in the shoe, we go from there. Again, weakness of one material is always the strength of another. All right, so that's the choice paradigm that we need to look at. All right, you're always going to have one that's better than another. Which one are we happy to work with at the point in time, and which is most important for this patient? Combinations, that's the key. Again, just a word of warning, materials research uses a wide range of methodologies. And they use a wide range of materials. They don't really study two materials with the same iris or the same materials. It's a very broad subject and very interestingly designed. No one kind of does a consistent study over time. So when we look at materials and what they say they do, we need to acknowledge that. All right. Is there a marketing benefit to changing the materials? Of course there is. Right? If I change a slight molecule to the material, I can call it something different and call it the new thing, and it works very well. Okay, what's the clinical benefit of that? If we go back and use our concepts of open or closed cell structures and how they're designed and woven, like in a vive, we can start to see the clinical benefits of those different things. All right, so from that point, there's no way we can recommend, okay, a clinical outcome, or we just can't do it from the research that's available. Okay, there's no consistency through there. So for us, what we need to look at, or what I consider, and what's your reasoning behind your material choice? What do you want to do? Where have I got? What anatomy is involved? What forces am I trying to deal with? Where is it? What shape have I captured? Again, pinch of salt with how much research you've been given. Most of the research that comes out of this area has been sponsored by manufacturers. Okay, we just need to acknowledge that. And again, the methodologies that you prefer to follow. Someone may like root, or Rootian concepts, and others may prefer the tissue stress theory completely. I'm a bit more balanced in, I think, well, I consider them all and see what's right for the patient at the time. Okay, endless possibilities, always relate it back to the patient. And remember, we are responsible for clear, documented clinical reasoning. Okay, even more so than ever before. I hope you've enjoyed this this little section and discussion. It is a very dry subject. More than happy to talk with any of you out there after this. And again, me and my generation and what I look at, I think those of you out there that are kind of 1970s onwards, you may see this, but I quite like this. May the ground reaction force be with you. Okay, cheers.